Hi folks, welcome back to the Core of Everything. Today we have Dr Matt Genge on the podcast, where we talk about meteorites, the origins of life, and even get into the Napoleonic Wars. First, we start with a quick shout out to Ben at Los Alamos National Laboratory, who sent us a picture of some petrified wood. So that's not wood that looks scared, it's just wood that's been fossilized and it looks absolutely incredible. So thank you so much, Ben.
Thanks,
and actually, you can see a piece of petrified wood on our Instagram as well, on a post that we did a few months back.
Do check it out. So Matt Genge is a senior lecturer at Imperial College London and an associate scientist at the Natural History Museum in London. He's a prolific researcher and science communicator. He's got a book called The Geological Field Sketches and Illustrations, a practical guide, published with the Oxford University Press. He's been on various media outlets, including Sky News, and is an expert in the field of micrometeorites. And above all these titles, he is also my PhD supervisor. So today I was on best behaviour, and we hope you enjoy the conversation.
Enjoy.
Because I'm a planetary scientist, if I found a fossil, then I would be terribly, terribly excited.
Yeah.
Yeah, on Mars or something like that. It's what we all dream of.
Yeah,
you know.
Yeah. No, I think people, when they think trace fossils, like a lot of people will be like a dinosaur's footprint from Jurassic Park, whereas actually they're sort of thin. A lot of them are just thin, tiny little. I don't know. There might be little holes in the ground or little tiny.
I'm great at imagining I found dinosaur footprints. Any random hole in the ground to me looks like a dinosaur footprint, and I sit there.
Even if it's a hole, it's just like a single hole.
I'm in the field with a paleontologist. Like, look what I found! Oh, come on.
Even if it's a single hole, it's just like one little long toe.
Yeah, just dipped in.
Well, obviously on a pogo stick.
But bouncing in exactly the same spot over and over again.
And there's a nature paper.
We were good for levels. So, because last time we were on, you came on a few weeks ago, and then we talked about lots of different things, but then the file became corrupt and we just lost everything. Yeah. So it's good to have you back on again.
Yeah.
I have to say.
It's always good to participate in such a professional organisation.
It's the first time it ever happened as well. Yeah. It was absolutely fine, wasn't it? And then suddenly, I don't know.
I blame the guy in the booth.
Yeah, the first time in the booth, wasn't it?
I think it was actually, yeah. That will relegate me back down to the floor.
Yeah, well, make sure you have you click record?
Everything, yeah. You can now see it as well, so full transparency.
Last time we spoke about Psyche mission. What's up with this? So Psyche mission, if anyone didn't know, is the NASA launched it 13th of October, wasn't it, last year? 13th, around that time?
Yeah.
And it was the idea was to head to a metal-rich asteroid. And
the biggest, 16 Psyche.
Okay.
I always had the E on the end.
Sorry.
I have no idea if that's actually right or not. Not if you're French,
no.
Probably. It's a really big asteroid, and I think it's around 120 kilometres in diameter. And I am making that number up. It's off the top of my head, but it's about that. And it's just, that's how it's such a massive object. And when you look at how much it weighs, so we use every year the Earth uses about 4 million tons of nickel, which is a significant amount of nickel, and that asteroid would provide us with nickel for about 800 million years. So that's how big it is. It's just incredible. But of course, the reason they want to go is we want to understand how that asteroid formed. So the idea is that metallic asteroids were the cause of larger asteroids, melted asteroids. So if you imagine you melt a rock in space, big rock, it melts all the way through, and the metal, being the heaviest, settles out to the centre of the asteroid to make a core, just like the metallic core of the planets. Now, of course, we cannot directly study the Earth's metallic core. Okay, seismologists can listen to it effectively with their seismic waves, but I'm somebody who likes holding rocks in labs and actually analysing them and looking at the crystals that form in them, because you can learn an awful lot about them, and we can do that with iron meteorites, but we still don't really know where those iron meteorites came from. We think some of them are cores and other ones aren't. And we're really interested in is this big lump of metal, is it the core of a very, very large asteroid which has been battered to bits? And it could be there's a complete surprise.
What are the alternatives there to it being a core?
One of the strange things about 16 Psyche is there's been some papers that have identified water on it. So by looking at it in the infrared in heat, water molecules absorb heat at certain wavelengths, so in the spectra, and we see those lines on 16 Psyche, and that's the last thing you would expect to find in the core of an asteroid.
Yeah.
You don't mean liquid water though? This is water.
No. Water in minerals.
Yeah.
So water can quite happily sit inside minerals, and then it's very protected. It's protected from space. It's difficult to boil off. So for good old mud, clay minerals, you've got to heat that to maybe 600 to 700 degrees before it releases its water. Think about when you were at school and you were making some disastrous pot for your parents as a present. The thing, or actually in my day it was an ashtray. Can you imagine them doing that today?
Teachers just like putting out a cigarette like that in the ashtray, carry on.
I think I made an ashtray in a shape of an Easter bunny that looked more like a T-Rex.
There's like something dark about that, isn't it?
There is, isn't there? And of course, you finish your monstrosity, and you give it to the teacher, and they have to shove it in an oven to fire it. And what you're doing there is you're getting rid of all the water in the clay minerals, and the clay minerals are turning into other minerals that tightly lock together, and they make it a nice, hard, solid object, which you can then use to stub out cigarettes in.
So where are we now with the Psyche mission? It's not at the asteroid, or it's how long will it take to get there, or where are we at the current moment in time?
So it's blasted off. It's going to take a long time to get there. So it's NASA, in order to be as efficient as possible, they choose orbits that encounter several other objects. So this one's going to come back around the Earth a few times in order to pump up its velocity so it can get to 16 Psyche. And then you get more out of the mission. So
like a slingshot?
Yeah, a slingshot.
Or a hammer throw. The one on the...
Yeah,
the ball on the string.
Yeah.
Well, not string, but on the chain.
Yeah.
I don't think a chunky person is actually involved in the NASA process.
It's like a paper airplane, you're just launching it. Okay, so you mentioned that there's water then present, locked up in minerals in this asteroid, but I think there's been a lot of papers in the past or discussion about water coming to Earth initially via a meteorite. I think that's under contention because there could be lots of ways water's on the planet. It could already been on the planet, locked up in rocks. In terms of the general science, what does it say about water coming to Earth, or how did it start via a meteorite?
Well, so when we look at a lot of meteorites, so the primitive meteorites, those that have never melted, quite a lot of them contain clay minerals. And clay minerals contain lots of water stored in the mineral structure. And if you heat them up, it releases the water. And it's an awful lot of water, so up to 12 weight%, which is a massive amount. And we know that the inner solar system, where the Earth is, was quite intensely heated in the early solar system. So most of the water should have gone. So even inside Jupiter's orbit, if you have water as ice in space, that ice then turns into water vapour, into gas, into steam, inside Jupiter's orbit. So it's difficult to keep it around unless it's already locked up in minerals. So certainly the Earth didn't acquire any ice. It was too close to the sun in the early solar system. There is a chance that there might have been some water locked up in the minerals on Earth. But even that's really difficult to do because a lot of the rocks actually melted. So especially when the Earth was small, as it was growing, as soon as it starts to melt, it loses most of its what we call volatile elements, things like water and SO2 and all the gaseous elements. And we know that if we look at the moon, so the moon is an object that we do have samples from, which is absolutely true. NASA did go to the moon. The best evidence being the Russians also brought back some lunar samples that look just like the samples that NASA brought back.
Some agreement.
Yeah, so some agreement. Why would the Russians ever do that? Yeah. When we look at the moon, the rocks from the moon, they are almost completely water-free because the moon had a very hot formation event in a giant impact, and all those hot pieces lost all their water. So we can expect actually the early Earth to have lost most of its water. So it needs to have come from somewhere, because we're not short of water on Earth, especially in the UK, especially today, where I got very wet on my way in. We're all sat here steaming, by the way, especially Jack, which is a bit disturbing. And you know,
my trousers are absolutely drenched, by the way.
Yeah, we just didn't want that level of detail, mate. We didn't want to know where the steam was coming from. So a logical place for this water to come from is from the small objects that hit the Earth later. So after you form the planets, the big planets like Jupiter and Saturn, they are the bully boys of the solar system, and they just threw objects around, and some of those objects hit the inner planets. And so the idea is that the water that was locked up in those objects, when they collide with Earth, is released and delivers late-stage water to the Earth and Mars and to Venus.
And is that released as water vapour that then is kind of held as a tenuous sort of envelope?
Yes, so as a primordial atmosphere, and then condenses and becomes involved in rocks and penetrates the Earth. What we haven't found yet is any direct match for the Earth. So we've looked at asteroids, we've looked at comets, and water's got a fingerprint, which is its abundance of deuterium, which is one of the heavy isotopes, the stable heavy isotope of hydrogen. So we can analyse that, and that shouldn't change with time. And so when we look at that in meteorites, we find that the asteroids have quite a wide range in deuterium compositions, and it doesn't exactly match the Earth. The average doesn't seem to match the Earth. Comets, the comets we've visited so far, also aren't a very good match. So the simple answer, which would have been to go to the asteroids and find that they had one number, and the comets and they had a different number, that unfortunately doesn't work.
So the alternatives then of water on Earth is what then? If it's not a meteorite or it doesn't quite match?
Well, it probably is. It's just we haven't found the majority of the objects that have accreted to the Earth.
Part of your research looks at micrometeorites.
Yes.
And also cosmic dust as well. So what is the difference between those sort of things and a meteorite?
Well, you might not be surprised to learn that a micrometeorite is a small meteorite.
Oh, yeah. Okay,
so you thought it was big, didn't you?
I thought it was huge. Yeah.
Because it's a bigger word. But it's really, they are dust particles in space, whereas meteorites are fist size or meter size pieces of rock. But they're essentially the same thing. They're just really tiny. That does mean they behave differently, though. Because, so meteorites as big pieces of rock, their orbits are largely controlled by the gravity from the planets. So they're perturbed into paths that cross the Earth. Whereas dust, and this is actually really cool, dust are affected by light from the sun. So they are actually pushed by light from the sun by a process called radiation pressure. Because photons of light actually have momentum. They have no mass, but they have momentum. It's above my pay grade to explain how that works. A nice Mr. Einstein once did it. And so as light streams away from the sun, these photons of light, they hit dust particles, and there's a slight pressure away from the sun. And that affects the orbits of dust. And a really even cooler effect is called Poynting-Robinson light drag, which is so science fiction.
Yeah, surely that's from Star Trek.
Yeah, light drag. And essentially the way this works is it kind of causes a friction in space. So dust particles whipping around in their orbits are slowed down by light. And as they slow down, to stay at a particular orbit, you need to be moving a particular speed. So if you slow it down, it's got to move inwards. And if you keep slowing it down, it spirals inwards. So dust particles in space, they slowly spiral inwards towards the sun. And that means they're much more likely to hit the planets because they're passing through the region where the planets are.
Yeah. These particles, these dust particles, must be tiny then to be affected by photons and.
Yes, well, they're fairly small.
Or at least very light.
You can just about see them with the naked eye. So they're just a little fleck. So if you think about a millimetre, everybody knows how big a millimetre is because we're all always looking at rulers. So about the biggest micrometeorites are a millimetre. Ones about 0.2 of a millimetre are the commonest. If you think about it, when you look at a ruler, that's about the width of a line on a ruler. So you can see them.
Yeah.
But that's small enough that they've got low enough mass that they're affected by light from the sun.
This is when they're travelling through space.
And that's when they're travelling through space.
So how do we... I mean, I don't think that when they travel through the Earth's atmosphere, they might get burnt up and...
Many of them do. So there's a famous quote from a NASA engineer who said, "I could get the Titanic through the atmosphere if I could find the right angle." Because heating during atmospheric entry is so dependent on the angle. So if the angle's too shallow, you'll probably bounce off back into space. Well, I say bounce. You shoot straight through, really. Whereas if it's too steep, you penetrate the atmosphere very quickly and you get to low altitude very quickly. And the atmosphere gets denser downwards. And the amount of heating depends really on the density and the speed that you are moving. So there's kind of a sweet spot. You got to come in at a really nice low angle, but you can't risk bouncing off. And these low angle particles are hardly heated at all. So they retain the most information. But even the steep ones can survive, and they form these tiny little magma droplets called cosmic spherules. So this other term that we use, cosmic dust, that's kind of like a bucket term. So the scientific term is really micrometeorites, but micrometeorite sounds a bit technical and weird, and it's quite a long word. So
and they're confusing. They can be massive. These
cosmic dust. The name really tells you what it is.
Was it one of your papers, Matt, that talked about this cosmic spherule that kind of had a grazing incident first and then entered the atmosphere?
Yes. So there was a really weird particle that had evidence for being heated twice. And if you think about it, if you drop something through the atmosphere, it only slows down once, so it should only be heated once. This particle had evidence that both of those were in the atmosphere, both of the heating events. But you can do that. So if a particle hits the Earth's atmosphere at a low enough angle, it shoots straight through the atmosphere. It slows down while it does it, and that heats it. But it can pass back out into space again, go into orbit around the Earth, and then re-enter the atmosphere. And then you get 2 stages of heating. And actually, it is possible that there's a small number of them, of likelihoods of doing it. You can go through the atmosphere multiple times. And each time you go through the atmosphere, it's called an aero pass. Every time you go through the atmosphere, you slow down a little bit more, and that makes the orbit smaller. And I've done simulations where you can have 7 or 8 aero passes.
And the particle would still survive.
And the particle would survive.
It's like a skimming stone, isn't it?
Yeah.
But the angle has to be perfect, no? Because if it's too shallow, then it might just go back out into space. And what about the effect of gravity? I'm surprised that even at a low angle, gravity doesn't take hold and just bend it back towards the Earth. It just skims off and goes back into space.
Well, it does bend it back towards. That's why it goes into orbit.
Yeah, okay.
I guess these things are moving at, it's like 10 times the speed of a bullet or something like that.
Yeah.
10 kilometers per second or higher. So, they've got so much velocity as well.
Wow. So as they enter the atmosphere, though, they burn. Well, a lot of them burn up. So in terms of some of the oldest micrometeorites, 2.7 billion years old, contain oxygen that we find.
A lot of them contain oxygen. Even iron meteorites have some oxygen, because oxygen it's one of the commonest elements in the universe.
Yeah.
The universe started off with lots of hydrogen and helium, and then the first stars appeared, and it started making lots of stuff like carbon. And then, as it proceeds, you start making lots of oxygen. And actually, the universe's oxygen is becoming more and more abundant, and it's slowly using up hydrogen and helium, and eventually it will use up the carbon too. Actually, there's more oxygen about now than there ever has been before. And oxygen's really interesting because it has 3 stable isotopes, and scientists like stable isotopes because these are, an isotope is an element, an atom of an element that has a different mass, but it's still the same element. And we like stable ones. By stable, we mean they don't decay away. So they should, if they're not being produced by radioactivity somewhere else, they should stay at the same abundance. And that means they're kind of like a fingerprint that you can use to trace where something has been, where it's come from. So that's one of the reasons we really like oxygen. But it's not actually the oxygen in the micrometeorites that it's not just the oxygen in the micrometeorites that's interesting. That tells us about which asteroids they came from. So, for example, if I look at any rock from the Earth and I plot up all 3 of its isotopes, so oxygen 16, 17 and 18, they all fall on a single line on a graph. So any rock from the Earth falls on that line. And interestingly, when you look at the Moon, they practically fall on the same line, which is excellent evidence that the Moon formed in almost the same place as the Earth in the solar system, that its impactor formed in almost the same place. But when we look at a lot of, for example, rocks from Mars, we have meteorites from Mars, they plot on a separate parallel line to the Earth. So actually, it's really easy to tell if a rock came from Mars. If it falls on the Mars line, it came from Mars. And some people have been caught out by this, because some people have tried to fake Martian meteorites.
Really?
You just analyse their oxygen, and you can tell it actually comes from down the road. So the oxygen that's already in micrometeorites is very interesting. But as they fall through the atmosphere and get heated, they can also gobble up oxygen from the Earth's atmosphere, which is great because that means it's storing that oxygen. It's sampling it for us. And actually, even today, it's really difficult to measure the oxygen in the Earth's atmosphere 80 kilometres above the ground. Because balloons don't go that high, planes don't go that high, rockets go that high, but they're moving quite fast.
Astronaut, like hand out the window,
Yeah.
just like that
With a cup.
yeah, come on,
But what this means is if we can find micrometeorites from the Earth's past that have fallen on the Earth millions of years ago, we can measure the oxygen in the Earth's atmosphere 90 kilometres above the ground millions of years ago. We can do geology on the Earth's atmosphere far above the ground. So cool. That is such a cool thing to be able to do.
Yeah. And tell you the history of oxygen, the development of the atmosphere over time. How does that correlate with the development of oxygen on 2.7 billion years old meteorites? How does that correlate with the Great Oxidation Event?
So we know that at first the Earth's atmosphere had very little oxygen, and that it was photosynthetic organisms like cyanobacteria that produced most of the Earth's oxygen. And like all trends, it became really popular in the Archean to do this, and there was a huge increase. Well, I say huge, it's still a few percent, but that was enough to radically change the Earth's environment, because oxygen is a very, very reactive element. And so, for example, in the Earth's oceans, most of the iron was dissolved in the water very early on. But as soon as you've got lots of oxygen around, the iron loves combining with oxygen, and they make these iron oxide minerals, really cool things like hematite, this bright red mineral. And so the iron rained out of the Earth's oceans. And we find these amazing rocks today called the banded iron formations, which have just got layer upon layer of hematite. And they're really beautiful. So you've got these red layers and these steely grey metallic layers. And they formed during this great oxidation event. And lucky for us, but actually, because, or lucky for industry, because that's the world's these are the world's biggest iron deposits. Mm-hmm. You get loads of them in Australia, in the Pilbara in Australia.
Yeah.
And they just cover like large areas, do they? Do they represent ancient oceans? Would it be?
Yeah, absolutely. And as a geologist, it's great fun to wander around in them, because so one of the problems with rocks from billions of years ago is they've got a very long history, and our planet is quite an exciting planet. So there's, if you look over billions of years, mountains get thrown up, rocks get folded, they get heated, they get transformed. And actually, so it's very difficult to find rocks of that age that are in good enough condition that we can actually really read the history. And the banded iron formations, certainly in Australia, they've escaped a lot of this processing. And they look amazing. I've wandered around in them, and you can, as a geologist, you can say, well, I can see the ripples that formed at the time on the ocean floor. So there were currents.
Incredible.
And you can say, and the water depth must have been about that. You can do all these things that you can do on much more recent rocks.
The way the current was going 2.7 billion years ago or 2.5 billion years ago.
Yeah, it's almost
incredible.
It is, and it's actually one of the greatest things about being a geologist is you can read rocks like a story, like a detective story, using nothing more complicated than your eyes. You just see shapes in the rock, and you know what they mean. You know what they can tell you about the environment at the time.
Well-educated eyes, because you can just make up a story, couldn't you? And then dinosaurs roamed around the Earth 5 billion years ago. No.
Making ashtrays out of clay.
Great callback. There's a correlation. The banded iron formations are currently being studied for, because they're well preserved and they haven't been metamorphosed or deformed, they have a preservation of the ancient magnetic field at the time. And they're currently being studied quite a lot, because around the Great Oxidation Event, where the rise of oxygen in our atmosphere and the flourishment of aerobic life that we have today, around that time, it's been shown that the magnetic field was a little bit weaker than it is today. And there's a correlation between, if it was weaker, more light gases, so hydrogen, would have escaped from the atmosphere, which would have allowed for the accumulation of oxygen in our atmosphere. But what I really wonder is, I wonder if there's a preservation of the magnetic field in these cosmic dusts, a droplet of hot rock. I wonder if there's a preservation of the magnetic field at that time.
There could be, certainly there could be, and you have to cut this bit out because that's now a research proposal.
That's actually
that's a really good idea. One of the issues is going to be that although they form in the atmosphere, we have recently discovered that a lot of them then subsequently become altered on Earth. So we're actually on the surface of the Earth through a process called diagenesis. And that replaces a lot of the minerals that formed in the atmosphere. But but there will be ones that are well preserved. We occasionally find really super ones that look, fantastic. They look like they formed yesterday. And that's because although most things get altered, most things get exposed to water, there'll be one or two lucky survivors who got sealed inside other minerals and protected. But it's finding those that's really difficult. Mark, he didn't used to wear glasses until he spent huge amounts of time staring down a microscope. So it's a lot of work to separate cosmic dust from sediments, because you might have, say, 10 particles in a kilogram of dust. You think about the billions of dust particles inside that kilogram. Separating those 10 is a bit of a challenge.
Yeah.
Welcome to my everyday life. Little circles burned on the back of my retina.
You see these little, every time you look at a screen or something, you see these little dots just like float across your eyes like that.
Yeah, you can always tell micrometeorites PhD students because they mutter to themselves.
They have that, and they also have a collection of Star Wars figurines on their desk. Amazing. So how does that, obviously we talk about aerobic life, but obviously there's a lot of, I don't know if there's a lot, but there's certainly some speculation to the origins of life on our planet, and maybe meteorites brought some kind of, some kind of form of life, or at least the building blocks for life on our planet.
Yeah, there are as many theories as out there as there are crackpots.
Do you count yourself?
I do count myself amongst that. Yeah, I've had some crazy ideas in the past. Or according to my reviewers. So the general idea is that that meteorites and cosmic dust could deliver the starting materials that helped life get started on Earth. So we know within meteorites, for example, there are a wide range of organic molecules. And I stress that does not mean they were produced by living things. You can make organic molecules without living things. It's like the difference between growing it yourself and making it in a chem lab. So you can make organic materials in a chemistry lab. And that includes things like amino acids and sugar. So really, really complicated organic molecules in meteorites that have never been inside a living thing.
And organics, we're just talking about like things made up of carbon, hydrogen, maybe some oxygen in there.
Yeah, some oxygen, some phosphorus, and then a whole bunch of micronutrients. And so the idea is that meteorites could deliver that stuff to the surface of the early Earth, and then it is there available for reactions, chemical reactions, because that's essentially what the origins of life was. It was a whole bunch of chemical reactions going on for millions of years over the entire surface of a planet, until all of a sudden one of those reactions led to a molecule that could self-replicate. And that molecule that could self-replicate was the first living thing. And we don't know what that reaction was. We don't know where it occurred. We don't know if there's only one way of doing it. But it's highly likely that the molecules we find within meteorites would have made that reaction more likely to occur. Because obviously, if you've got the starting materials, you've got the building blocks. If you put a monkey in a room with a whole bunch of Lego, at some point they're going to produce the Eiffel Tower. If you don't give them the Lego, they never will make the Eiffel Tower. So by having the building blocks, it makes it much more likely to produce living things. And what's kind of suspicious is this coincidence that the origins of life occurred really quickly on Earth. So there is evidence for life by at least 3.8 billion years. There's some evidence for it a bit earlier, about 4 billion years, isotopic evidence. And that was a period where the Earth's surface really was not very suitable for living things. It was being impacted all the time by asteroids and comets. So we know there was a large amount of delivery of material at that time. Conditions were very harsh. And yet life still got going. And to me, that's the main reason for believing the origins of life is spontaneous if you have the right materials and some areas where you've got the right conditions.
I wonder if it's a case of the materials are already here on Earth, but actually because of the chaos of the meteorites impacts, it would create the conditions, temperatures, pressures that would just trigger the first molecule, rather than it brought the materials. I wonder if it's more of a...
Well, the kinds of pressures and temperatures you generate in impacts are huge. So that's not very good for organic molecules. They break down really easy. But what they can do is so around impact craters, the residual heat from an impact crater can generate what are known as hydrothermal cells, a hydrothermal system. And that's hot water percolating through these warm rocks. Now that's good for chemical reactions. Because with chemical reactions you want temperature. Well, chemical reactions always run faster and significantly faster at high temperature. But the limiting factor is molecules have a certain temperature stability. So if you have the temperature's too high, that molecule will break down.
So you need it to be just right.
Yeah.
Did any of these impacts, I know that you can get this ejector, might be one of those crackpot ideas, but did it not just cool the atmosphere slightly because it just blocked out the sun, created a nice little cooler atmosphere that life could flourish?
At the surface, but you block out the sunlight, you'll trap the heat in.
Right. Yeah, it's a crackpot idea.
No, it's just it's not a rubbish idea. It's not up to your usual standard. But it's not as straightforward.
Which maybe is quite a nice segue to talking about dust that might come from other sources, such as volcanoes, and the effects that this could have. I think you wrote a paper where there's some relationship between dust and Napoleon.
Before we get into this, because I've read War and Peace recently, and Tolstoy talks a lot about necessity and reason versus free will and consciousness and the unpredictability of everything, and why the invasion of Russia was sort of unsuccessful, as well as a very harsh winter.
I love the way you just threw in. I read.
Yeah.
Well, I can edit that bit out because it sounds
elevating
pretentious.
the podcast.
It sounds
That'll be our opening kind of.
If anyone has any take on Tolstoy or Dostoevsky, please let us know. And also there was other studies that show that, well, not studies, but other theories that Napoleon, around the time, it was either Waterloo or it was Russia, where he had a cold, he had the sniffles, which affected his decision making. Can you imagine? That's the reason why there's a downfall of Napoleon, was because it's like, medic, I've got a runny nose. So the Battle of Waterloo was obviously incredibly muddy and harsh conditions, but you say there might be a geological influence.
Yeah, so this came about because so I was thinking about volcanic ash, and so there was this long-held view that volcanic ash cannot enter the Earth's mesosphere. And the mesosphere is the third layer of the atmosphere. So you get the troposphere at the bottom, the bit we live in mainly, the stratosphere, which is the bit we sometimes visit if you're going on a very high atmospheric flight. And then above that is the mesosphere, which is hardly an atmosphere at all, a bit rubbish. And that's the layer of the atmosphere that contains the ionosphere, this electrically charged area. And very handy for us, because that's the one you bounce radio waves off of. We couldn't have worldwide radio if you didn't have an ionosphere. Anyway, so the idea is you can't get volcanic dust to be above the stratosphere into the mesosphere, because volcanic dust is lofted by buoyancy. So in a volcanic plume, the hot gases are moving upwards and it's going up like a balloon, and it's dragging the dust with it. And at the top of the stratosphere, there's this temperature inversion that prevents convection through it. So you can't, things will not, a balloon won't float up through the top of the stratosphere. And I thought, yeah, but there could be other forces. And I realised that dust is affected by electrical charges. And so you've got a dust that's charged, and you put another large charge near it, it will push that dust particle away. And volcanic plumes are highly charged. You may have seen photographs of volcanic lightning, of a volcanic plume just covered with lightning. So they can be highly charged. And if the individual dust particles are charged too, which we know they are, then the dust on the top of the plume should be lofted up. And so my idea was that could give it an extra kick to get into the mesosphere, to push it up through that layer that is a barrier to dust, and it could get into the mesosphere. And so I did some pretty simple simulations just to trace where individual dust particles could get to given realistic charges, and just to see whether they could reach the mesosphere in an appropriate amount of time, the time that eruptions occur over. And the answer was yes, they can. They can get up to the very high in the mesosphere to the ionosphere in a matter of hours to days, which is short enough that that's within the timescale of a large volcanic eruption. And I realised that because those are delivering charge into the mesosphere, that could have an effect on the ionosphere. And the ionosphere is really important because there is a constant voltage between the ground and the ionosphere, and it's huge. It's like 30,000 volts. It's massive. And you can measure that charge on the ground. You can actually see that the ionosphere must be up there. And it's really important in the formation of clouds, because clouds form from nuclei, tiny little dust grains and droplets of liquid that grow to make larger droplets of liquid that eventually collect to make clouds. And the behaviour of these nuclei is affected by that charge between the ground and the ionosphere. So my idea was, if you're delivering all this charge to the ionosphere, you could seriously muck up the ionosphere. And actually, there have been measurements showing disturbances of the ionosphere during volcanic eruptions. And so my hypothesis was, during a big volcanic eruption, you could stop the formation of clouds if you lose the ionosphere. Mm-hmm. And then the amount of water in the atmosphere goes up, and as soon as the volcanic eruption ends, it rains. And it rains. And it just so happened that there was a large volcanic eruption that ended shortly before the Battle of Waterloo. And people, noted how much it rained in Europe after this eruption. And of course, it's just nonsense, really. He didn't. It wasn't just because the ground was wet and he couldn't deploy his cavalry that he lost. He lost because he picked a fight with all the countries in Europe. And whenever you do that, you lose.
And he had a cold as well.
And he had a cold, absolutely. The Austrians, the Prussian army turned up just in time and saved the day. And interestingly, the British, the British won the Battle of Waterloo. That was all propaganda at the time. That was the Duke of Wellington. So apparently there was a big reconstruction of the Battle of Waterloo was commissioned in London a few years after the battle, that people could visit and view this historic victory. And the Duke of Wellington made them remove most of the Prussian troops.
So harsh.
Yeah.
Well, is that in the Natural Portrait Gallery or something like that? You can see a painting of him. Like,
no, it was actually a model. I'm not sure where it is now and what happened to it. But it was at the time it was documented that he was like, there's too many Prussians on this field of battle.
They can be on the side making the cups of tea or something.
But Prussia being the country that was described. Prussia is less of a country and more of an army with a country attached. But what was really, I thought was really interesting, and I didn't discover this until after I wrote the paper, and after the paper was published. I was reading the Royal Society report on Krakatoa, the eruption at Krakatoa, which of course is another really big eruption that occurred in the 1880s. And there's just one line in the report on the climate, and where the scientist very casually says, and it is remarkable how little it rained globally during the Krakatoa eruption.
Oh, wow.
I thought, I wish I'd seen that before.
Yeah.
Wow. I think Victor Hugo mentions how bad that time, the weather in Les Miserables, doesn't he?
Yeah.
As well.
Yeah.
Yeah.
What a cultured man you are, Jane.
No, I read that quote off Matt's website. So yeah, for any listeners, you can check out Dostoevsky, Tolstoy, Victor Hugo, and Matt Genge as well. Getting a nice diverse picture of the summer. What was it again? The year without a summer.
The year without a summer.
Oh, I'd say the winter without a summer, but that's every winter, isn't it? Matt, thanks so much for coming on again. Really appreciate it. Sorry about the last time. Mark, save this now so we can get it done.
Fab.
All right. Cheers everyone for listening. Thanks.
Bye.